three-phase 3-wire delta circuit with a residual current transformer includes the following components. Firstly, lone L2 and L3, which are the three-line conductors. Secondly, A, B, and C, representing the three load terminals. Thirdly, the RCT or residual current transformer. And fourthly, G, which is the ground connection, although not shown on the load side in this particular configuration. Now, let's delve into the concept of residual current transformers, or RCTs. RCTs are designed to measure the vector sum of the currents that are flowing through the three phases of the circuit. In essence, they are monitoring the overall balance of the current within the system. Any difference in current between the phases is a key indicator. It suggests an imbalance which often points to a fault condition somewhere within the circuit. The sensitivity of the RCT allows it to detect even small imbalances, providing an early warning system for potential problems. Now, let's discuss what it means when the neutral is not regrounded on the load side in a three-phase 3-wire delta circuit. In this type of circuit, the neutral point, often designated as N, is intentionally not connected to ground on the load side of the circuit. This is a deliberate design choice that has significant implications for how the circuit behaves, especially in the event of a fault. Because the neutral is not grounded on the load side, there is no direct path provided for fault currents to easily return to the source. This is a crucial difference compared to grounded systems, where a low impedance path to ground is intentionally created. The absence of a direct return path for fault currents can have several consequences. One of the most significant is the potential for severe equipment damage if a ground fault occurs. In a grounded system, a ground fault would typically result in a large fault current flowing back to the source, tripping a circuit breaker or blowing a fuse to quickly interrupt the circuit. This rapid interruption minimizes the amount of energy that is delivered to the fault location, reducing the risk of damage. However, in an ungrounded delta system, the fault current may not be large enough to immediately trip a breaker. Instead, it can circulate through the system, potentially causing damage to insulation, windings, and other components. This is because the voltage to ground on the unfaulted phases rises to line voltage during a ground fault. The lack of a low impedance path to ground also means that the voltage on the ungrounded phases can rise significantly relative to ground. This increased voltage stress can further exacerbate the risk of insulation breakdown and equipment failure. The absence of a grounded neutral can also make it more difficult to locate the source of a ground fault. In a grounded system, tracing the fault current back to its source is often a straightforward process. However, in an ungrounded system, the fault current may take multiple paths, making it more challenging to pinpoint the exact location of the problem. Despite the potential drawbacks, ungrounded delta systems are sometimes used in situations where it is critical to maintain continuous operation. For example, in some industrial processes, an immediate shutdown due to a ground fault could have significant economic consequences. In such cases, the ungrounded system can allow for continued operation until a planned shutdown can be scheduled to repair the fault. However, it is essential to have a robust monitoring system in place, such as an RCT, to quickly detect and locate ground faults in an ungrounded system. This allows for prompt action to be taken to minimize the risk of equipment damage. To summarize, the absence of a grounded neutral on the load side of a three-phase 3-wire delta circuit means that there is no direct, low impedance path for fault currents to return to the source. This can increase the risk of equipment damage if a ground fault occurs, but it can also allow for continued operation in certain critical applications. The use of RCT and other monitoring devices is essential for detecting and locating ground faults in ungrounded systems. It is important to note that working with ungrounded systems requires specialized knowledge and precautions. It is essential to consult with qualified electrical professionals and follow all applicable safety regulations.